Hey, all right, let's get started today. Our lesson today is on trees. So this is both a new data structure and a new opportunity for us to practice with this new problem-solving technique that we introduced yesterday, recursion. So, to me, these topics are sort of quite connected, in the sense that recursion as a problem-solving technique, as we pointed out yesterday, is completely general. There are no problems that you can solve without recursion, without using recursion, or let me put it that way. There are no problems that recursion can't be used to solve. In fact, there are entire programming languages that don't have any looping constructs. However, in programming languages that do allow you to write imperative, iterative code, like the code we've been using so far that uses loops, some problems lend themselves more naturally to recursion than others. So, for example, last time, I think in our walkthrough, we looked at the difference between a problem that's sort of looking for a value in an array. And to me, that's an example of a case where the iterative code is much more natural once you start to learn how to think about iteration. However, trees are a data structure that is very natural to work with using recursion. And in fact, in this lesson, when we go through, and we'll do this in the future, next couple lessons, we'll be getting a lot of practice with recursion in binary trees. When we actually went through the example using a binary tree, it turns out that there's no imperative equivalent. There's no iterative equivalent that we could actually produce. We'll get there. We'll eventually be able to show you how to do this, but show you, techniques for working with trees that use iteration, but they're actually pretty difficult, and they end up being a lot more cumbersome than just using recursion. So, again, I don't want to reprise too much of the material here. So, in the lesson, we go through the definition of a tree, a particular type of computer science data structure. There are really two complementary reasons that we use trees in computer science. One is to model data in the world that has a tree-like structure. And frequently, that data has, trees are good for representing hierarchies. And there are examples of this in the lesson where we talk about different types of real-world data, real-world systems that match up nicely with this tree data structure. So sometimes we use trees because a tree is a good fit for the underlying data. There are other times that we'll talk about where we use trees because trees are actually a good, the tree data structure enables certain algorithms that are more difficult to implement on things like lists and arrays. So there are some times that we store a collection of items in a tree because we then get some nice properties for certain algorithms. So you might remember one of the maps. Java has two map implementations, at least two. I think there may be more. There's the hash map, which uses a hash table internally and implements that similar to how we've done things in the past. There's also something called a tree map that implements a map using a tree. And again, on that point, we're not using a tree because the data is structured as a tree. We're using a tree to implement this map that we've talked about in the past, where we're able to store mappings from keys to values. The implementation of map uses a tree internally because it produces certain operations on that tree end up having some nice properties. Trees are a topic that if you go on in our curriculum here at Illinois, you will definitely see plenty more of. You'll see them again in 173. I think if you take our new course 128, if you're a non-major, you might see a little bit of them there. And then you will definitely see them in 225 as well, in some different variants of trees. So trees come up a lot in data structures, not only because they are a good fit for certain types of data, but also because they allow us to implement certain algorithms efficiently. All right, so now our tree that we're going to work with, our binary tree class that I'm providing that you can import now on the playground, more or less has this. So first of all, we're going to work almost exclusively with binary trees. A binary tree is a tree, but where we have the extra limitation that any node in the tree can have at most 2 children. The reason that we work with binary trees is the data structure is just a little bit simpler. So imagine if I had to, and we could do this, we could create a general tree data structure, but then every node would have to have a list of children. With the binary tree, what's nice is that you'll see here my binary tree class has a left child and a right child. That's it. I don't need to store a whole array and to iterate over things. So it makes certain things a little bit cleaner. It's not hard to generalize the stuff that we do. So learning how to count nodes in a binary tree, learning how to implement various recursive algorithms on top of binary trees. If you wanted to take those algorithms and then generalize them into a tree that allowed more than 2 children, it's pretty straightforward. It's really just sort of the concepts here that we want to get. So this is our binary tree class. We go a little bit about over a little bit of where this sort of comes from. And then we start implementing some algorithms. So we go through in the lesson, we look at doing a sum over a tree as our first example of tree recursion. And tree recursion introduces some patterns that we're going to see as we continue to do more examples of this type of problem. So kind of what represents the base case, how do we make the problem smaller, and how do we combine results together. And those are kind of the 3 ingredients that many recursive algorithms have. And certainly on a tree, the other nice thing about trees is that there's sort of like this mental map that you can start to build up where you can sort of visualize what's happening as things go along. Okay, I'm done with my intro. Sorry that somebody missed multiple choice questions. Yeah, today's quiz was MC heavy because we had sort of a fair amount of content to cover. So I would say that score is probably completely fine. All right. Questions about trees or recursion. So for the next couple days, we're going to get more practice with these concepts. We're doing more trees tomorrow and recursion, and then we'll do even more tree recursion on Thursday. So this is a week of tree recursion, and we'll do kind of a mix of this where we'll do a couple of problems together in the lesson, and then we'll have a homework problem. And we'll get you to the point where you're doing some pretty cool things with trees. There's some pretty neat things that we can do with the tree, including passing data structures through our recursive calls and stuff like that. So we're starting out slow, but you guys will get some practice doing some pretty cool stuff with trees, and then we'll actually do a little bit more with trees after Thanksgiving. So all right, so I'll pause here and allow you guys to answer ask some questions. About trees. We can certainly go through some of the examples that we talked about with trees. I'm happy to talk about, go through some of, look at today's recursive problem and how to solve that. In terms of the one we went through in the lesson, we can talk about, try to give you more of a sense of what's happening when you use recursion as a problem-solving technique. I'm very flexible. Again, this is one of these parts of the class where we're really sort of trying to hammer a particular concept, give you lots of practice with thinking recursively, since for some of you this is a new idea. And so we're going to prepare you the same way we always do, with lots of examples, lots of practice. All right, questions. I will hang out here answering as many questions as people are interested in asking. Yeah, great questions. So a linked list on some level is a tree where every node has one child. Exactly. And so if you think about it, actually this is a fun problem to look at. I mean, on some level, yeah, so actually let's do this. And I'll continue to take questions, but let's just do some little fun implementation thing, right? So let's go back and think about our list class, right? So we had linked list. We had this item class where every item had we'll just let this be, and then an item next, right? And then let's see, I'll just implement the add method quickly just so that we have something to work with. We have an item start. Is this going to compile or yeah, it's fine, okay. And then we'll say, okay, so I need some way to create one of these. Say public linked list, object values. I need a way to add things at the beginning, so I'll do public. Well, I'll just leave this private for now because it doesn't fully work. You know what? I don't even need this. I'll just do it right in here. So we'll say for object value. Oh, I need to go backwards though. Okay. And I is equal to values dot length minus 1. I is greater than or equal to 0. I minus minus. And we'll say start is equal to new item. And then we'll say I need an item constructor here too. Item set. Oh, I hate Java sometimes. It's so verbose. Well, you know what? Is a record here? No, I just don't know the record syntax well enough yet. I need to get there because that'll help me preserve my sanity next semester. All right. And we'll say value is equal to set value. Next is equal to set next. Great. And then we'll do item. So this is values I. The next is going to be start. Remember, I'm adding things backwards at the beginning. And then I'll say that's fine. So there we go. So now I've got, let's see if this will work. And I'll say linked list is equal to new linked list. And I'll say give it an array of strings. See if that works. Okay, it seems to work. All right, so yeah, so we just quickly, ginned up this little linked list class, and so the question is, can we write some recursive algorithms on this list? And the answer is sure. How about we print the list? Okay, and so this is one of those, so let's write something recursive just for fun. We'll have this return a string. We'll have it be static. There's a couple different ways to design this. Print. And I'll just call this toString, and then linked list, right? And so the idea here is let's say I want to print the items in the list, and I'll just print them like all on one line. Well, this is a little bit tricky here. Yeah, how about this? I'll have a string. Well, maybe I'll just print them one at a time, just directly using println, right? So iteratively, I would walk the list using a loop. We showed you how to do that in the past. But I can also do this recursively, right? How do I do it recursively? Well, what I say is if the list is null, and actually what I want to do is I want to do list.start is null. And actually, sorry, what I need here is I need to do this. I need to start this on an item. Sorry, something's banging around. Must be my wife upstairs. So I'm going to start this on an item. I'm going to say if the item is null, then this is an empty list. And so I'll just return, and I'll make this void. Call this print list. Otherwise, what do I do? Well, how do I make the problem smaller? So the idea is that every item has a next item, which leads to the rest of the list. So what I'll do is I'll print this item. So I'll do system.out.println current.value. And then I'll print the rest of the list. Print list current.next. All right, let's see if this works. So I'll do linked list.print list. And I have to do it list.start. There you go. So this is a recursive. So you can work with lists recursively. That's really the point here, right? Now, again, so this is and actually for fun, let's do two versions of this, right? So here's our iterative list printing, print list, iterative, print list, iterative. Oh, I broke my recursive step. Oh, and this isn't even iterative, this is recursive. Right, brain is like running it a slower speed than usual today. This recursive, that works fine. Now let's try the iterative version of this, right? So how would we do this iteratively? We would say, just write our loop, right? This is our list walking loop for item current is equal to, and I'll call this start here rather than current. It's a little bit easier. Current is equal to start, current is equal to current.next. Oh, sorry, current not equal to null, current is equal to current.next. Print the value. Oops. There you go. Right, so that'll work. And now let's try our other version of this just to make sure it still works. There you go. Yeah. So two different ways of printing a list, one that uses recursion and one that uses a loop. Obviously, we have showed you how to work with lists iteratively using the reference walking loop. One of the reasons, and maybe this just has to do with my systems background, one of the reasons that we've done this is because when you look at systems code, some of you will go on and take courses like 241 where you'll do some systems programming in a language like C. You'll probably actually work with a list in that language. You don't see a lot of recursion. You just don't. Those languages don't support it very well. So the code that I've seen, the code that I've written, the code that I've worked with that works with linked lists and languages like that never uses recursion. It just doesn't. I mean, I know that there are these recursion weenies that, but they're not writing C code anyway, right? They're off writing Haskell and Clojure. So, but anyway, so I feel like and I also think it's great practice with references. And so we have showed you with lists how to work with them iteratively. And the nice thing is with the list, because every item only has one next reference, it's much easier to write this loop. Now, as a challenge for the reader, I'm not going to attempt this because it's impossible. I would encourage you to think about how you would write a similar loop to iterate through a tree. The answer is you can't. And the problem is at every node you have two possible paths, right? With a list, iteration is easy, right? I just go one after another following the references. With the tree, at every step I have potentially two references I need to follow. There is a way to do this. I'm not saying it's impossible, but it's much, much trickier than the approach that we use with lists. But yeah, you can definitely work with lists recursively, and on some level you could argue that a list is a special case of a tree, right? A tree with every child only has one ancestor. On some level though, trees are themselves a special case of a different data structure called a graph. If you take this to its logical extreme and you start talking about lists as a special case of tree, I don't know really if that makes a lot of sense, right? Just because the thing that distinguishes lists and arrays is that they're ordered data structures. If you think about a tree, what's the order of the nodes in the tree? Well, we can start to have conventions about how to order nodes in a tree, but they're just that. They're just conventions. A tree, lists and arrays are linear data structures. They put things into order. A tree does not really associate the same metadata with every item. Like I said, you can come up with a convention for how to order nodes in a tree, right? So let's go down and look at one of these trees, right? We could say, okay, well, maybe I start at the root node, I order them by level, and then I go left to right or something like that. But that's just sort of it's a convention. If you looked at a tree, if you gave someone a tree and you said, tell me what order the items are in the tree, you'd get a bunch of different answers because there's a bunch of different ways of doing this. If you give people an array or a list, right, that's an ordered linear data structure. So the ordering is much more clear, and I shouldn't say much more clear. The ordering is what the data structure is doing. trees. So I think all to say that even though a list is on some level a special case of a tree, removing that, limiting to one child creates now a linear data structure which provides order, and so it really ends up in a different category. Yeah. Yeah, but good question. Other questions? There's a couple good ones to get started. So, other questions? Weird. Why is that what's showing? Oh, something happened here. It's weird. Cat did that. Other questions? I'm sure there's things you guys are curious about. I'd love to talk about them, so fire away. Mrs. Ziz. I had her here a minute ago. I don't know where she ran off to. Let's see. Hey. Am I coming? Oh, I'm making Jason. Come on. She's being shy. Sorry. She may show up here. I tried to get her up here a minute ago. My laptop's nice and warm, and I thought she might enjoy that, but I don't know. She's. We left a window open all night last night, and I think she really found that exciting. Yeah, the other thing that I think is throwing her for a loop is that we have this automatic feeder for her that we have on a timer, so it's supposed to go off every morning, and there's something wrong with it, which is. Oh, there she is. Hey, you want to come over here? Hey, meow, come here. Come here. All right. Oh, meow, huh? You're talking to me. What's up? I know, something broken with your feeder, but I'm still feeding you. Maybe the fact that the feeder is broken will make it a little more clear to you who's responsible for the food dispensing. You know, you should give me more credit for that. All right, you want to hang out? Oh, I'll put you down here just in case you want. Stay put. Last time you hit some keys on my keyboard. Off she goes. All right, well, briefly. Other questions? She's around. I think she's back at the window. The leaves to her are super fascinating this year. I don't know why, but she's just totally curious about the leaves. And falling, it's very exciting to her. There's some squirrels out there pushing them around. She finds that to be extremely interesting. So she's a cat. What can you do? All right. Other questions? I was actually thinking about this the other day. We'll see. Yeah, I mean, so if you haven't been following what's been happening, there's sort of some interesting developments in this space. Specifically, so just to set some context here, it's totally fine for off-topic question. I think we're sort of out of questions today. So one of the things that's driven the really, rapid improvements in computer speed and power over the past 3, 4 decades has been our ability to make transistors smaller and smaller. So as time has gone on, and electrical engineers have figured out how to make smaller and smaller transistors. Those transistors allow us to put more computing power on the chips that we use. That then turns into faster clock speeds, more powerful instructions, and that's sort of what we refer to colloquially as Moore's Law. By the way, Moore's Law is not a law. Physicists would not call it a law. It's not a law of the universe. What Moore's Law describes is a trend that the semiconductor industry was capable of maintaining over a period of time, where computer speed or computer power was doubling, like I think every 5 years or something like that, and it was largely driven by improvements in transistor density. Recently, that trend has started to run into some fundamental limitations that really have to do with the physics of extremely small devices. Along the way to where we are now, Intel, which for many years was considered to be sort of a leader in this space and really drove the improvements in transistor technology for a long time. So essentially, what's been happening is you make chips with a certain size transistor, and then along the way you're kind of planning for how to get to the next size, which is even smaller, and then you're planning for how to get to the next size, which is even smaller. The next step for Intel, and some of the terminology here I'm not super familiar with, but is what they refer to as the 10 nanometer process node. So this is a new line of chips that are supposed to use a transistor of a particular size. And by all reports, Intel has been having a very difficult time with this particular set of chips. They're behind schedule. They are having difficult times with the quality of some of the transistors that they've been making. And so they've had a really hard time getting to this particular design point. In the meantime, some of their competitors, like ARM, for example, now there's debates about how exactly you measure stuff, but ARM has actually been working at an even smaller process node. And on some level, it seems like basically Intel had a long run as the sort of undisputed, I would say, driver of innovation within this industry. And it seems like they are kind of in the middle of a big stumble right now. Time will tell if they can pick themselves up and continue on to, produce even more advanced chips. But for right now, ARM is having a more smooth transition down to even more powerful chips. And I think my suspicion is that some of Apple's decision here is motivated by this, right? So Apple for years has been using Intel processors. I suspect at least some of their move away from that is some of it's probably driven by additional configurability, right? So Apple can now very tightly couple Apple's always done this, right? So Apple has always been, in the market for selling very, very tightly coupled systems. This is not to let Microsoft off the hook, but some of the lack of problems that you have on Apple devices that sometimes are considered to plague Microsoft-driven devices has to do with the fact that Apple controls the entire product. They control the software, they control the hardware, they control the casing, they control all the components. So, if you think about one of the things that makes software very hard, particularly software that runs devices, is dealing with lots and lots of different configurations. With Apple, they don't have to worry about that because they control the entire machine configuration. Windows has to run on all sorts of different machines. Microsoft doesn't make hardware. So with Apple, it's like you're buying the entire thing from them, right? They made the software, they made the case, they didn't make the hardware, but they selected all the different components and they made sure they all worked together, right? I've actually built now a couple of machines that are called Hackintoshes, where you basically take a machine that is not Apple hardware and you install Mac OS on it. And one of the only ways you get this to work is by being very, very, very careful about the components you select. And if you don't get them right, really bad stuff can happen. So I built a Hackintosh once, and because I had picked the wrong processor, the whole thing wouldn't work, right? Because I just got a processor that macOS wouldn't support. And they don't care, right? Because they're like, once you start building a Hackintosh, you're way off the map to them. They're never going to support what you're doing because you're supposed to buy the hardware from them. So I think in taking the chipset and putting that inside their control is just another, to me, it feels like a natural move on their part. One of the other things that's happening, I think that's driving this too, is that one of the ways that we're going to continue to see performance gains from computer chips is that they are going to start becoming less general purpose. So on some level, previous computer chips, the idea was that they could perform any type of computation. They weren't sort of specialized around doing certain things. We've seen increasing specialization within devices already. If you open up your phone or your laptop, actually, you're not going to find one processor. You'll probably find a dozen different processors in there already. There's this one really expensive, very powerful general purpose CPU, but there's already lots and lots of different other processes that are there to do very specific things. So there's a set of processors there to render graphics, right? This is known as, that has its own name. It's known as a GPU. But even past that, there's all these other little processors. For example, there's probably a specialized chip there to do audio decoding, right? It's just such a common task. People use their computers for music. There might be a chip in your computer somewhere that's only job is to basically take like MP3 files and M4As and other things and just decode that. And what that means is that the main chip doesn't have to do this. So anyway, all to say that I think that part of the move is probably due to Intel's struggles, but part of the move is also so that Apple, in an era of increased sort of chip customization, can have that part of the machine now be under their control. So they can sort of do these vertical integrations where it's like a particular part of their software works a particular way, and if they need specific support for that within the CPU, they can now do that, right? So we'll see. I mean, I'm actually kind of excited about it. I think it'll be interesting. Maybe because I'm also just sort of like, having been an Apple customer for many years, the worst machines that I've bought from them have been the last couple. And I just think like something's running out of steam. So it'll be interesting to see if this helps mix things up a little bit. How many homework problems do you think we'll have this semester? I don't know. We'll see. I mean, yeah, we're overrate at this point. I don't have any plans to change the pace, so we'll be doing, I guess I can probably predict the number. Let's see here. Let me go peek at what I've got here. What's it called? It's called, right. All right, so you guys are doing your 67th homework problem today. There are 2 more on tap for this week, so that'll get us up to 69. We'll do 4 more next week. That'll get us to 73. We'll do 4 more the week after break. That'll actually maybe 5 that week. Who knows? At least 4. That'll get us to 77. And then maybe a few more. So maybe we'll get to 80. I like the number 8. So maybe if I play my cards right here. Actually, I think we can. I think we'll get to exactly 80 now that I think about it. So 69 before break. 4 more the week after break. Wait, 69 this week. 4 more next week, that's 73. 4 more the week after break, that's 77. And there are 3 days left in the semester at that point, Monday, Wednesday, Tuesday, Wednesday. So if I lay out homework problems on those days too, that'll get us to exactly 80. And we'll probably do that because I would find that highly satisfying, just because of my interest in that number. When we sit down and do the final grading, we will adjust the number of drops to be commensurate. So we'll add a few homework drops because the homework drops that we provided were scaled to the target 65. Given that we're going to shoot by that by a little bit, we'll bump up the number of drops as well. So yeah, homework problems are great, right? How did we get here? We got here because we gave you weekend problems for a while, and that was not something that we had done in the past. So that's sort of how we ended up with more than usual. Although, to be honest, I think we've usually ended up more in the range of like in the 70s rather than 65. I don't know. I should update the number. So I think it's better to have more than it is to not make that number. So other questions? These are good questions. All right, if there are, I wonder where this went. Kind of a nice little breeze blowing through here today, so I think it's exciting her. All right, if there are no other questions, then I'll let you guys go. If you're in the Champaign area, it looks a little overcast today. I think that this might be the last super warm day. Oh yeah, we're gonna add a rating feature. That's the next thing on the, yeah. So we'll get there. Yeah, the next part of the NP, which will be a 1-week checkpoint that will get us to break, which will be to add a rating component to the page. I also think I'm going to throw one little backport on there where I'm going to have people display a little bit more information about the course. The main reason for this is because of how we set up the test suites. This time it was possible to pass some of the tests without really doing what we wanted. And so we're going to fix that for next time. So the next checkpoint's 1 week. It's fast. It's right before break. I don't want to overload people, but the goal, the end goal here is to get to the point where there is a rating component that's available. So there'll be that'll be an opportunity for you guys to add some UI to the component, and then also a little bit more route on the client on the back end. So on some level, it's a very similar process to what we did, except we're going to use post this time rather than get, because you'll need to send some data to the server. So it'll be fun. All right, I'm going to wrap up there. Tomorrow we'll do more practice with recursion. So I'll see you tomorrow. Now that I think about it, I mean, tomorrow and Thursday I may do office hours in lieu of the walkthrough, because the lessons are very hands-on. So there's a huge amount of new content to talk about. There's just problems to work through together. If that's the case, I'll let you guys know. But enjoy the last day of the really unusually warm weather, and I'll see you tomorrow.